Okay, so welcome guys to the post-contest discussion of Codeforces Global Round 26. And I am Abhinav Kumar and this is TLE Eliminators. Let's get started with the first problem. So in the first problem, we have string splitting. Define the range of a non-empty array to be the maximum value minus the minimum value. For example, the range of 142 is 4 minus 1 is equal to 3. So it's given the definition of range of an non-empty array. So we'll just take the maximum value and subtract the minimum value. We'll get the range. So now it's given that you are given an array of length n and n is greater than equal to 3. It is guaranteed that A is sorted. So if we are given a sorted array. Now what we have to do, you have to color each element of A red or blue so that the range of red elements does not equal the range of blue elements. That's the first condition. And there is at least one element of each color. That's the second condition. So we need to color this array into either red or blue, every element into either red or blue, so that it satisfies these two conditions. And if there does not exist any coloring, you can report it. So if there are multiple valid coloring, you can print any of them. So that's the question. So if there are no possible coloring, we have to print no. If there exists a possible coloring, we have to print yes, and then just print a string which represents which one is colored what. R represents red, B represents blue. So likewise, we have to print. Okay, so let's take a look what we can do here. Okay, so like in the question, it's given that we are given a sorted array, like 1, 2, 4, 6, like that. We are given a sorted array. And then this array, we have to color it into either red or blue. So let's suppose I colored this and this as red, and let's suppose I colored this and this as blue. So now the conditions it should satisfy is first is the range of red should not be equal to the range of blue. Okay. So we are actually like dividing this arrow into two parts. One would be the red colored ones, other would be the blue colored one. So if we color like this, the red one would be 2, 4, and the blue one would be here 1, 6. Now we need to calculate the ranges of these two, and these two should not be equal. That's our first condition. The ranges should be unequal. So if we do like this, the range of this red would be 2, 4 minus 2, and range of this blue would be 6 minus 1, 5. And they are unequal. So this is satisfied here. And the second condition is that at least one element of each color. So that's the second condition. So there should be at least one element which is colored red and at least one element which is colored blue. So this red array and blue array should none of them should be empty. Just these two, we have to satisfy these two conditions and do our coloring. Okay, and we are given this given array is at least of size 3. It's greater than equal to 3 and is greater than equal to 3. We are given that. Okay, now let's see what we can do here. So we are given that we have to color this array into red and blue so that their ranges are equal. So like first, let's see when would we get a no as our answer, that we cannot get two different ranges. We cannot partition this array into two different ranges. When would that happen? So like clearly that can only happen if all of the elements of the array are equal. Let's say we have 2, 2, 2, 2, 2. All the elements are 2. Then whatever we pick for red or blue, all of for red also, all of them would be 2, 2, 2 only. For blue also, all of them would be 2, 2, 2 only, whatever we pick. So the range of both of them would be 2 minus 2, 0, 2 minus 2, 0. So in this case, the range would always be 0 and always be equal. So for this particular case, we'll give our answer as no. Okay, so this is one of the special case we can just consider initially only. That if all the elements of the array are equal, we can just directly print no here. But what if all the elements are not equal? Then can we always divide this into red and blues? Let's see. So we are saying that we have considered this case where all are equal. Now we are saying that all the elements are not equal. Let's say we started with 2, then maybe more 2, 2, 2, and something after that we got a 3, 4, and we got 4. We always have a sorted array. So the smallest would be at the start and the largest would be at the end. So the first thing to check is if all the elements are unequal, it means the smallest would not be equal to largest for the given array. Okay. So it means these two elements are going to be different for sure. Okay. And one more thing we can notice here, that what we have to do, we have to make the ranges unequal. So let's see what our ranges are. So let's see if we have only one element. If an array has only one element, what would the range of that array be? It would be the highest in this would also be 2, the lowest would also be 2. So it would be 2 minus 2 equal to 0. So if we select only one element as red or only one element as blue, the range of that would always be 0. This we can just notice here. Okay, if we select at least two elements, that it may be, then it may be 0, it may be greater than. But if there is only one element, then that element is only going to be the maximum as well as minimum. So range would always be 0. And if we have an array where all the elements are not equal, we don't have all the elements equal. That is, the first is not equal to last. So here we can actually make a range greater than 0 by selecting the first element and the last element into the same bucket, like both of them red or both of them blue. So what you can do here, you can just select the first and last element, both of them. Let's say we selected both of them as blue, blue. Then the range of blue would definitely be the largest minus smallest. And this would definitely be greater than 0 if all the elements are not equal. Okay. So then for the blue case, we can get a range greater than equal for blue by selecting the first and last element. And for red, what we can do, we can just select one element from middle, like anywhere from this part, just select any one element and make it red. Now, what would the range of red be? It would be equal to 0. So this blue is always greater than 0, red would be equal to 0, we would get unequal. Okay, so this is one way to solve the problem. And what about the remaining elements? Like those which are not selected by, we can just assign it to blue because it won't affect its range. Its range would be the largest minus smallest, and all those middle elements would be in the middle. Okay, so like that, we can solve this problem. So what we have to do, we have to just so for red we can just take any element from the middle, and it's given just n is greater than equal to 3. So we will always have at least one element in this middle part. So we can just suppose take the second element as red always and remaining element as blue, and we are done. So what we can do, so whatever, let's say you have this array, just you have to take the first element as blue, the last element as blue, that's for sure. And from the middle, any one element has to be taken as red. Let's say the second element is red. Then take the remaining elements as blue. And so this coloring would be our answer simply. So just simply color the second element as red and remaining element as blue. It would be always okay to do that. So like that's what I'm doing here. You can see my code now. Okay. So like first, the first thing which checked here is are all the elements equal? So it's given in the question, we are given a sorted array. In a sorted array, if the A0 is the smallest element, AN minus 1 is the last element, which is the largest. If the smallest is equal to largest, it means all the elements are same. Then we are going to just see out no. This Y at 0 is a hashtag defined. It just means see out no. So we are going to do see out no in this case if all the elements are equal, and we are just going to return. Otherwise, we can always have an answer. So we are going to do see out yes. And after that, what I'm doing, the first element is red, second blue. So okay, in the explanation, I made the second element as blue and remaining as red. In the code, I'm doing the second as like in the explanation, I did second as red, remaining blue. Here I'm doing second as blue and the remaining red. So it doesn't matter, you can do anything. Okay, so here I just made the first red, second blue, and remaining also red. Okay, so I'm just like printing like this, red, blue, red, blue, blue, blue. So if I just run this would be my the thing I'm printing. So we can have multiple answers. So red, blue, red, 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 blue, red, 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 blue, red, red, red. Likewise, I'm always printing. Okay. So that's the first question. I think it's quite clear. If you have any doubts, you can share. Okay. Okay. So let's move on to the second question now. Okay. So what we have in the second question, which is large addition. A digit is large if it is between 5 and 9 inclusive. A positive integer is large if all of its digits are large. So first we are given the definition for a large positive integer. What is a large positive integer? Which has all the digits large. It means if all the digits of a number are between 5 and 9, then we are going to say this is a large positive integer. Okay. Now what is given? You are given an integer x. Can it be the sum of two large positive integers with the same number of digits? So that's our question. So like we are given a positive integer x, something like this, and then we need to tell, can we have two large positive integers of with having the same number of digits? So we have to have two large positive integers having same number of digits, and the sum of those should be equal to this x we are given as an input. So if we can do this, we are going to return yes. Otherwise, we have to return no. That's the question. Okay. So like let's understand. Let's take the first case where it's, let's say we have 1337. Okay. So what we have to do, we have to select two numbers. Those two numbers should be large numbers, and the sum of those should be this. So what can we do here? Let's say we have something, we have to sum up two large numbers to obtain this. Let's say you have 5, 5, 6, and 6, 6, 7, anything like that. So if you have any two large numbers and sum of those, and you need to get this, so can you make it? That's just the question. Okay. So now let's try to identify what all what all things we can get from this. So first thing to identify here would be, like if you have a number of, let's say, four-digit number. Okay. So when can you get the sum of two numbers as a four-digit number? Okay. So either those two numbers would be three-digit plus three-digit, and like they would overflow and give one carry and make it a four-digit number. That could be case. Or the two four-digit numbers get added up to a four-digit number. Okay. Both of these two numbers should have same number of digits. So which case would it be? Now we are given that it is a large number. It means all the digits are between 5 to 9. So when we are adding up, let's say you have some digits here. Let's say you have two three-digit number. Both of them are large. They are in the range from 5 to 9. So when you add two large numbers, so there at minimum it would be 5 and 5. So at minimum 5 and 5 would get added up to become 10, and one carried would get carried here. This is the minimum case. And at maximum, what can happen? We have two three-digit numbers, and at max there could be 9 and 9. And when both of them get added, it becomes 18. One gets carried, and it becomes like this. Or maybe if you had a carry one from before, then one more would get added and it would become 9. Okay, so at max we can have this, at minimum we can have this. So like you can notice, and there would be like two more digits coming from here. So if you add two three-digit large numbers, you get a four-digit number, any number. Okay. So the first thing to notice is, if the input is given as a four-digit number, we are going to have two three-digit numbers that are going to get added up to give this value. Now, the second thing we can notice here, what would like always we took the minimum and maximum case. Let's see like what would be the minimum three-digit large number. It would be 555. So if we take the minimum case, it would be 555 plus 555. So this would be 1 carried 1 and 1, 1, 1. So the sum of this would be this. At minimum, the sum of two large numbers is this. At maximum, the sum of two large numbers would be what? 999 plus 999. This. Okay. So can you notice something in both of those numbers? So whatever two large numbers we add up, the range of that would lie in between these two. At minimum, we are going to get this. At maximum, we are going to get this. And you can notice in every number from 1110 to 1998, the first digit is always 1. Can you notice this? Okay. So the first digit of the number would always be 1. This the input should always be such that the first digit is 1. If it is not 1, we cannot have any possibility of that number to exist as the sum of two large numbers. Can you get this thing? So the first conclusion we are going to write is that the first digit should be 1. If it is not 1, we are directly going to return 0 in this case. So return no in this case. Okay. So this is the first conclusion we drew from here. Okay. Is this conclusion clear now? So now let's see more. What more conclusions can we draw from this? Okay. So since we are adding up like two large numbers, okay, and we know like if we have a four-digit number, we are going to require two three-digit numbers to get added up to make that four-digit number. And the first one is going to be 1 year. This much thing we already know. Now let's see what the unit digit would be. So this is the unit place. So whenever we add two numbers, we start from the unit place. We start adding from the unit. So let's say you at minimum what you can have here 5 5. They are going to sum up and give a 0 here and 1 carry. Okay. So minimum case would be 5 plus 5 and we get a 10. So this 0 would go to the unit place and this 1 would go to the carry. Okay. And at max what we can have? We can have a 9 9 here, a 9 here, a 9 here. 9 9 would get added up to make it 18, 8 here and 1 get carried. So this is the thing we can have at max. So at max we can have 9 plus 9 which give us 18. So this would be the unit digit. This would be our carry. So like you can notice whatever we take in the unit place, we are going to have in our resultant unit place a number in between 0 to 8. Okay, the sum is going to be in between 10 to 18. So for carry, we are definitely going to have 1 as the carry. That is for sure. In every case, we are going to have 1 as a carry. And the units place we are going to have is going to be in the range of 0 to 8. This is the first thing. Can we have a 9 in the unit place? If we have a 9 in the unit place, can we have it? To get a 9, at max we can have 9 plus 9 here, which would give us 18. We cannot have a 9 here. Okay, without carry it would be 4 plus 5, but 4 is not a valid large number. So you cannot have it. So if you have two large numbers, you cannot have 9 on the unit place. So this is our second conclusion, that can't have 9 in unit space. So this is our second conclusion we drew. Now let's look at the other places what we are going to have. Now we are sure that the carry is going to be 1 from the unit place always. So we are going to have a 1 carry here. Now what would this digit be? So even if you have at minimum what you would have a 5 here and a 5 here. So this sum would be 5 plus 5 plus 1. It would give us 11. and we would have 1 year and one carried. So we would have at least 1 year. Can we have a 0 year? So we have one from the carry, and at minimum we are going to add a 5 and 5 to make it 11. We cannot have 10 here so that it would be 0. So we can never have a 0 in these cases. You can just notice this from me. Okay, so like, and what would be the maximum range here? If you have a 9 and 9, we are going to have 9 plus 9, 18 plus 1, 19. So you would have a 9 here and 1 10. So for the tens place also, for the tens place, if you look at it, the minimum condition would be 1 plus 5 plus 5, which is going to give me 11. So 1 would be at the tens place and 1 would be carry. And the maximum case would be 1 plus 9, where we are going to get 19. This would be the 9 would be the tens place, 1 would be carry. So we can conclude the carry is always 1 in this case as well. And the range of tens place would be from 1 to 9. So we can have any numbers from 1 to 9 in the tens place, but we cannot have a 0 here. So that's our third conclusion. And you can just notice if we go to the hundreds place again. In the hundreds place, we again have a carry 1 and the same to same situation. So again, we would for the thousandth place, we would have a carry 1. So same situation for all. So we can just write it like this. First conclusion was that the first digit should be 1. This we have to make sure. Second thing, that the units place should not be 9. And the third thing we can write, that the remaining places, which is except unit, this should not be 0. That's our third conclusion. So with these three conclusions, if we make sure that none of these three happens, then we are going to return yes. Otherwise, if any one of these condition does not satisfy, we are going to return no. So that's simply how we are going to solve this problem. You can look at the code now. So if like first the special case I'm considering, if n is 1, so like if we the sum is given as like we are going to have 1 as the sum, so two large numbers cannot get added up to give a sum 1. Okay, so like we are taking the input as a string, and 1 means the number of digits is 1. So if you have number of digits as 1, it means you are going to require two 0-digit numbers to get added up to make it 1. As we concluded, you cannot have a 0-digit number. For this case, we are going to see out no in this case. Okay, this y and 0, it just means see out no. Okay, you can just look at this. And we are going to return. Then if the first digit of the number, first digit of the input number, if it is 1, it's okay. If it is not 1, we are going to return 0. It means we are going to see out no in this case if the first digit is not 1, as we wrote in our first conclusion. Then what we wrote in our second conclusion, that the units place should not be 9. So if the units place is 9, so we are taking the input as a string. So the last digit of the string is our units place. So if this is 9, we are going to see out no. And the third conclusion was that remaining places should not be 0. So we are going from the index 1 to index n minus 1. Okay, just before index n minus 1. So all the middle elements we're considering. The first element we consider, it should not be 1. The last element should, the first element should be 1. The last element should not be 9. And the middle elements. So this is a for loop for the middle elements except the starting and the end element. So these, if any of these are 0, we are going to return no in this case. And if all of these conditions are satisfied, we are not returning a no in any of the case, then we are going to just see out yes. Okay, that's our code. So I hope this second question is clear to you. Okay, if you have any doubts, you can ask. Okay, so now we are going to move at the to the third question, which is C1, which is the easy version of the C problem. Okay, so like in the traditional these C1, C2 problems in easy and hard versions, you get the same question and the constraints are different in most of the cases. But here in the C1 and C2 problem, the problem statement is slightly different, not the constraints. Okay, so we are going to look at them separately. So first, let's look at the C1 problem. So what we are given here, you are given an array A of length n. You start with C equal to 0. Then for each I from 1 to n in increasing order, do exactly one of the following. Okay. So what you are given an array of length n, and now you are going to start with, we are going to take a variable C and you are going to start with 0 in it. And what you have to do, you are going to move from 1 to n in increasing order. So you are going to move in the array from the start to the end and do exactly one thing. Either set C to C plus AI or set C to C plus AI mod, where this is the absolute value. So either you can add AI to C, or you can add AI to C and then take the absolute value of the resultant. Okay. These are the two options that you can do here. Now, let the maximum final value of C after the procedure described above be equal to K, find K. Now you have to find the maximum final value that you can obtain for C. Okay, so now let's look at it, what we have to do. So what we are given as input, we are given an array. Okay, so we are given an array of length n. So now what we have to do, we have to take a C which would be equal to 0. Let's say we have 1, -3, 5, something like that. Okay, let's take an example. Anything like that. Okay. Now what we have to do, we have to start with C equal to 0. We have two options. We move to the first element of the array. Either we can do C plus 1, which will result 0 plus 1 into 1, or we could do C plus 1 and mod it. So mod of 1 would again be 1. So in this case, both of our options are going to result in 1. So this is our C. Now we are going to move to the next index. So we have C equal to 1 here. Now what we can do, either we can do C minus 3, and so 1 minus 3 would be -2, or we can do C minus 3 mod. So it would be mod of -2, which is 2. Either we would have -2 after this case or 2 after this case. Now we would mean, let's say I took this one as 2. Okay, I took the mod. So with C equal to 2, we are going to move forward and we are going to take move to the next element, which is 5. So with C equal to 2, either you can do C plus 5, which is going to give you 7, or C plus 5 mod, which is also going to give you 7. So let's say we take C equal to 7 and then move to the next element, you do plus 4. Both of them are going to result in 11, 11 only. We take C equal to 11 and then you do -10. It would result in 11 minus 10 would result in 1 only in both the cases. So likewise, and then you add plus 3 and plus 6. So you get 10 here. So in this case, only decision we had to make was in this. Either we select 2 or -2. Had we selected -2, we would maybe got a lesser number. So that's what we have to decide, which option to select so that we get the maximum possible number. We have to select the options in a way so that we get the final resultant value of C we get this should be maximized. So now how can we maximize? Okay, if you see what is the final value of C, if you select only option 1, if you select only option 1, then the final value of C would be, let's say I'm denoting it by C final. This would be the summation of AI. Just simply we are going to just add up AI. That would be the C final if we select only option 1. Okay, now what happens when we select option 2? So while doing this, let's say you started with C equal to 0, then you added the first element, it made C was made as A1. Then you added the second element, you got A1 plus A2. Then you added the third element, you got A1 plus A2 plus A3. Likewise, you moved and you got summation of AI at the end. Okay. Now this was for only option 1. If you select option 2 instances, so let's say you got here, and here instead of option 1 you selected option 2, then you would get a mod of this. So if this value was positive, then it would make no difference. Either you select option 1 or option 2, there is no difference. But if this value is negative, then it is going to just invert its sign. So if it was negative, A1 plus A2 was negative, it's going to make it minus of A1 plus A2, which would be a positive value. That's what it is going to do. Now, moving forward, it would become minus of A1 plus A2, then plus A3, like this. If this value is negative, again we can apply operation 2 here and make it positive, invert the signs. Okay, so what happens when we invert this sign? So we need to get the maximum profit out of this. So we need to maximize our final element. That's our target. So whenever we apply the operation 2, what's the like profit we are getting? It's like you are turning a negative number. If it was minus 5, you are turning into plus 5. You are going to get a profit of plus 10 actually from here. That's the thing you can notice. Now, if you made minus 5 to 5, then you moved up. So now to again get some profit, you need to move it down to a negative number. Then only you can have any profit from the operation 2. If it is a positive number, you're not going to have any profit from the operation 2. So if this gets reduced again to, let's say, minus 1, then you can make it 1 again and have a profit of plus 2. But let's suppose I'm saying I'm applying this operation 2 times. The operation 2 I'm applying 2 times. One, when the sum was minus 5, we made it plus 5 by applying the operation 2. And then again the sum got reduced to, let's say, minus 1 at some stage, and we applied operation 2 and made it 1. We got a plus 2 profit by applying operation 2 here. Now, if you look at this plus 5 was reduced to minus 1. It means you had a net minus 6 here. So if we had not applied this operation, then this minus 5 would get minus 6 and become minus 11. So instead of minus 1, we would have minus 11 if we had not applied this operation. Okay, we would have minus 11 here instead of minus 1 if we had not applied the second operation at this stage. And from minus 1, if we apply the operation 2 here, we can get a plus 11, which would be a profit of 22. So by applying 2 times, we got plus 10 plus 2, a profit of 12. But here we got a profit of 22. So what you can notice from here, if you are applying the operation to 2 times at some case, so here the number has become negative. You applied the operation 2 and made it positive. And if you are applying it again, it means the number has got reduced. So if the number has got reduced again, so instead of applying this operation, if it would have reduced here and become like more negative, so the more negative it is, the more profit you would get. So the first intuition you can get is the maximum profit we can obtain if we apply the second operation only one time. The first conclusion I'm giving you is you you would never apply the second operation two times, because if you are applying it two times here and here, it means after applying the first time the number has got reduced. So it would have been better to let it reduce more so that it becomes more negative and you get more profit from that. That would be a better case to apply it in the second time only, not at the first time. So always we are saying that if you are applying it two times, it's not the most optimal way. You should apply the operation to only one time. Like one more way to imagine this, if you have not understood it clearly, let's say we can draw a graph kind of thing. Uh, this is representing zero, okay, and we have one, two, three, likewise numbers moving on, minus one, minus two, like this. Okay, initially we are starting with zero. Let's say the first element of the array is one. We would move to one if we add plus one. Second element is two. We move to two. Then we, let's say, had a second element was one. Okay, so we moved from one to plus one. We moved to two. Now let's say we had a minus three. We moved minus three here, and we moved to minus one. Okay, so the graph, if we are only applying the first operation, the graph would be something like that, like that. Okay. Now, when you apply the second operation, if you are in the positive range, you it doesn't matter you apply first or second operations. We are considering only first one. Whenever you are in the negative range, you can apply the second operation and make it how much it is below the zero line, that much above the zero line. If it is minus one, you will make it plus one. If it is minus two, you will make it plus two. Okay. So by applying the second operation, from anywhere you can just move this graph up, and if it is moved up, this whole thing which we are getting, this whole graph, this would move up by this much places, so the graph would somewhat become like this if you apply the second operation here. Okay, so let's say you applied it here and the graph moves somewhere like this, and even after applying it's again going to the negative case. Okay, so you can apply one more time there and move it up. But what I'm saying, you would apply it at the minima point wherever the it is most negative. You would move it up, and so that you have some positive thing going ahead, and you go positive only and increase only. If after moving up, if you are reducing it again, if it is getting reduced more, if this is not the minimum point, let's say you had some point which was less than this, it means you are reducing the value. So it would have been better to apply the operation here so that you get more profit. So from this graph, like we can understand that you will always apply the second operation once, and that would be applied at the minima point of the graph. Okay. If you have not understood it, no problem, but this thing would be used in the C2 problem. Okay. This conclusion. Okay. If it wasn't clear here, we are going to discuss again on the C2. So it should be like this much, it should be clear that the second operation is going to be applied only once. So if we get this conclusion that the second operation will be applied only once, if we get this conclusion, now how can we write our code? Like we can simply now just brute force all the ways of applying the second operation. So it's going to be applied once. So it would be either applied at the first index or the second index or the third index or the nth index. Either one of the places the second operation would be applied, and in the remaining places the first operation would be applied. So let's say I applied the second operation at the ith place. what would my final sum be? Okay, so this is somewhere ith place. I applied the second operation here. Okay, what would my final sum be? So till here I applied the first operation, so we get the sum up till here, and then we added up the AI in that and made the absolute value of that. So it's actually the sum up till I and the absolute value of that. Okay, absolute value of the sum up till I, and then remaining elements we are going to just apply the first one operation. So we are going to just sum up some of those. So actually we can write it, if we are applying the second operation at the ith position, our final C would be the summation of AI from I equal to, let's not write it I, the summation of AJ, let's write it AJ, from J equal to 0 to I, the absolute value of this plus the summation of AJ from J equal to I plus 1 to N, okay, or N minus 1 if we are taking a zero based indexing. So this would be my final C if we apply the second operation at the ith position. Now, can we compute this in O of 1? So like you will know, we can use something called prefix sum. So if we have computed the prefix sum of this array, the prefix array of this array, then through the prefix array we can just directly compute the sum of any range in O of 1. So if you use the prefix array concept, we can compute this sum in O of 1, and this we can compute for each I. So brute force means we can have this I from 1 to, from, if we are zero based indexing, from 0 to N minus 1. So for each I, we are going to go and compute this sum, and the final C we are getting, we are going to take the minimum of those, all of those. So that would be our, the maximum of all of those, that would be our maximum final C we can get. Okay. So exactly that's what I am doing in my code. So you can look at it. We took the input. This is the input part, and then we are going to just compute to prefix and suffix sums. The suffix were not needed here. You could have done the prefix of n minus prefix of I to get the suffix, but I have computed suffix also, and there is no problem. Okay, so this is how you compute the prefix sum. Prefix I is prefix I minus 1 plus AI, and this is how you compute the suffix sum. Suffix I is suffix I plus 1 plus AI. And one of our answer would be if we apply the second operation 0 times. Okay, maybe you don't apply the second operation. So, or at the end, after the, at the last index. So then you're just going to sum up all the elements and take this absolute value. So this can be one of our answer. And then we are going to take the I from 0 to N minus 2. Okay, there we are going to go and compute our sum. It would be the absolute value of the prefix I. So till I we are going to sum up and take the absolute value. This would be absolute value of prefix I, and then the suffix of I plus 1. So the, for the remaining values we are going to, the sum of the remaining values is going to be suffix of I plus 1. So this sum we get, and then we are going to maximize our answer with this sum. Okay, we are going to take the maximum answer and see out that. So that's a like very simple code for that. Only thing to notice here was that the second operation is going to be applied once. If you can notice that, then this code becomes easy to write. If you can just think of a little prefix, suffix sums, that's the small thing you have to think about after that. Okay. So this was the problem C1. If you have any doubts in it, you can ask. Otherwise, we can move to the next. Sir, can you explain the use of suffix sum? So, okay. The suffix sum actually, like without suffix sum also, we could have done this problem. If you see what conclusion I wrote here, this is the sum we need to calculate. Okay. So one way was that you write this final C as equal to, what would be the sum of this? This sum from 0 to I, it would be prefix I. Prefix I stores the sum from 0 to I. its directly prefix I and the absolute value of that. Okay. And then what is this sum? This sum is the sum from I plus 1 to n minus 1. So if we have an array, this is I, you have to sum this part. So either you can write it as prefix of n minus 1, which would be the sum of this whole, and subtract this part from it, which would be minus of prefix I. Okay, so either you can write this here, this would be the sum. So without use of suffix array, you can write this, or you can, what I did is just, I computed a suffix array. So prefix array was, so prefix I used to store the sum from 0 to I, suffix I stores the sum from end to I. So suffix I just represents, so if you have an array, this is ith position, suffix I stores the sum of this much thing. Okay, if it is clear. So I just wrote here, instead of this thing, I wrote suffix I plus 1. Suffix I plus 1 just gave me the sum from I plus 1 up till end of the array. Okay, so we can do both of these things here. Is it clear? Okay. Okay, so if you have any more doubts in this question, you can ask, or we can move on to the next question now. Okay, so let's move to the C2 problem. Okay, so in C2 problem, this is an extension of the C1 problem only. The initially the problem statements up till here is the same. Like you are given an array of length and you start with C equal to 0 and apply either this operation or this operation. Now, here what you need to find is, let the maximum final value of C after the procedure described above be equal to K. Find the number of unique procedures that result in C equal to K. So in the C1 problem, we had to find this K, which is the maximum final value of C. Now here what it's saying, if let's suppose you found out this K, now you have to find the number of unique procedures that result in C equal to K. Two procedures are different at any index I. One procedure choose option 1 and the other procedure choose option 2, even if the value of C is equal for both the procedures after the turn. So what does procedure means? It means the sequence of our selection. Like if we are selecting option 1 always, our procedure like it would be 1 1 1 1 1 1. If we are selecting the option 2 somewhere in the middle, 1 1 1 1, then there's a 2, then there's 1. So we have to find the number of ways number of procedures we can for this sum to be equal to K. Okay. And we have to print the answer as modulo this. Okay. So now how can we compute this thing? Now the first thing to notice here is, let's say some special case where like the sum is always positive. If you just start adding from here, you add up, you add up, you add up, you end somewhere here, and the sum is always positive. It never goes in the negative range. In that case, if it is positive, whatever you add, either you apply option 1 or option 2. For the positive case, both are same. Okay, both would be same. So you can apply either of those. So in every step, you would have two options. So if there are n steps, there would be 2 into 2 into 2 up to n times steps. So it would be 2 to the power n simply. So if for this case where both option 1 and option 2 are the same thing in every step, that is, we are never going to get a negative number as our sum, then we can just directly write our answer as 2 to the power n, and this modulo m, we have to just, this would be our final answer, because for every step we had two options. This is just a standard base case, or like just a base case. Now let's solve the problem for a general case. Okay. So like in the C1 problem, I was explaining you something like this, some conclusion like this. So this conclusion, like while giving the contest, I also, while solving C1, I got this conclusion first that the second operation would be applied only once, and I wrote that prefix code and got submitted. But when I looked at the C2 problem, so if we are going with that conclusion that the second operation is going to be applied only once, that only once we were taking for our convenience that it would be applied only once. But let's suppose there is some positive number. Here we were saying that we are applying the operation 1 only, but we could have applied operation 2 also here, although it would not affect our result. But for counting the number of ways, we would have to consider both of them. So we would have to find in what positions we have two options, apply either operation 1 or operation 2, and in what positions we have to just apply only operation 1 or only operation 2. Okay, that thing we have to look for finding the number of ways. Okay, so that the thing that the second operation is going to be applied only once, this is not going to work for the number of ways thing, because once it would be definitely applied, but for the remaining where we are saying operation 1, for the cases where we have positive numbers, we may have operation 2 also there. So we need to count those also. Now, how can we count those? So, like for the that prefix thing, one thing is if you do like that. Okay, let's say at some index I, you got this, and like this is not a good graph for that. Let's say you had something like this at some index I, you applied the second operation and made it this. So, uh, what would be the total number of ways to do this? So till here, when we are in the positive range, we have two both the options, either apply operation 1 or operation 2. We can apply any of them and it won't affect because the result of both of them would be same. So we would have two options. The uh, till here, okay, two options for each of the positions. When it gets to the negative range, so if we apply operation 1 here, we are going to get to negative. If we apply operation 2 here, we would reach the positive range. So to continue here, in this range, we have to apply operation 1. And for this particular point where we are applying operation 2, we have to apply operation 2. So this is fixed. We have only one option, apply this operation 1. And this is fixed. We have only one option, apply this operation 2. After that, when we are moving here, here also we are in the negative range. So here also, if we apply, okay, so like when we applied operation 2 here, we move the graph up. Okay, we move to the positive range here. So now when we are in the positive range now, we can apply either operation 1 or 2. So two options here. Let's say even after this, we moved again to the negative range. So this is the thing I was trying to explain before, that the position where you are going to apply your second operation, you are going to move your graph here. This would be that point such that after applying this, you are never going to get back to a negative range, because this is going to be your minima point where you are going to apply. If you can get back to the negative range, it was better to apply the operation to here instead of applying it, because you would have been more negative here. If you like look at this, if you didn't apply the operation to here, you would have been more negative here. So that would be more beneficial to you. So that's the like conclusion. The thing we are drawing for computing this is that if you represent your sum, your prefix sums in a number line, where you are starting with 0, and then as you add up. Okay, so this is the graph for your prefix sum. You add a1, you move somewhere in. You add a2, you add a1, you move somewhere here. You add a2, you move somewhere. You add a3, you move somewhere here. A4, then a5. So something like that you would move. So something like that would be the, if you like draw it on a graph, kind of something like that would be a graph. So from this, if we notice, if we apply only operation 1, the final point we are getting is going to be our final value of C. And through operation 2, what we can do is just select any negative part and make it positive and just move whole graph up. So we have to just decide which point would be that point where we are applying operation 2 so that we get the maximum profit. So what would that point be? What is our profit by applying operation 2? If the point is, let's say, -5, we are reaching a +5, our profit would be 10. What is this 10? 5 minus -5. So if this point was -x, our profit would actually be 2x, if you notice it. So the more negative this point is, so the more the absolute value of this x is, the better our profit would be. So where would we apply our operation to? We would apply at the minima point. That's what I am trying to explain here. Okay. So if you have some point, let's say you moved here and then you moved here somewhere. If you have a minima point, this would be the point where you're going to apply your operation to for the maximum profit. Only once at this point. Okay. Only once means here you are definitely going to apply. And then other operation two would be at where our graph is positive. So at those point where we are getting positive, we can apply either of those operations. Okay. And after the applying operation two, this would move up somewhere. And then this whole graph, this thing would be like retraced. This thing would be retraced above. Okay. So, and for this new graph, you are going to find all those positions where the graph is above the zero, where the graph is positive. There you have two options, either apply operation 1 or operation 2. And where the graph is below the zero, that is negative, there you have only one option. Except this point you will only apply operation 2, and except this point at the remaining points, you will only apply operation 1. So you can just count the number of positions where my graph is positive, and 2 to the power that many position would be my answer. If there are x positions where the graph is positive, 2 to the power x would be my answer, modulo m of it. Okay. Now, one more case we can have here is, what if we have two minimas? What if the graph is something like this, and we have like this point and this point, both are minima and both are equal. So you can apply this operation to either here or here. Both would give you the same result. If you apply this operation to here and move this whole graph up, you will like get something, you will reach here. And if you apply this operation to here and like move this graph up here, okay, this much, you will again reach this same point. Now, what would you do? So you have to find the number of ways. So you would first consider this point once. What would be my number of ways be when we apply the operation to at this point? If you move the graph up at this point, so that plus what would my number of ways be if you apply the operation to at this point? This would be my, like this would be my answer. Okay. So let's see, if I applied the operation to at this point, what would my answer me. How can I compute my answer? So the first thing I told, if this is a minima point, if we move the graph to the positive axis here, and this was the minima point, it means there was nothing below this line. So if we move the whole graph up, there would be nothing below this line. It means after applying this operation to moving the graph up, then in the remaining part, all of them would be positive always. All of them would be always positive. So the number of positions we have remaining, we can just count those positions where we have two options. So if it is positive, we have two options here. So count of these many positions plus the count of those positions where we have positive. Okay, just remove this count. So if we get this count as CNT, then 2 to the power CNT would be the number of ways if we move the graph up from here. Those would be the number of ways to make this final answer. And then again, we are going to compute it for the second minima case. For this case, so it would be the sum of this part plus this part plus the remaining part. That would be our CNT for this case. So it would be 2 to the power CNT2. I'm saying to CNT1 here. That would be the number of ways for this case. So our final answer would be like 2 to the power CNT1 plus 2 to the power CNT2, and then just model. So how can we compute this count? So we just need to compute this count. Okay. So first, like we would store a prefix array. Let's look at the code and understand what we are doing here. Okay. First thing I did was computed this prefix array. Okay. Suffix is not used here. I just copied from the C1 problem. That's why it's written here. It's not used here. Okay. I computed the prefix array first. Now we have to like kind of imagine this graph. What this graph is. This graph is the graph of the our prefix array. This is the graph of our prefix array. So in this graph we have to work with. Okay. Now I computed this prefix array. Now we are going to store this CNT. Now in CNT, what we are going to store is we are going to compute the prefix prefix sum of the count of numbers which are greater than zero. So let's say I'm applying the operation here. What I would need if I'm applying the operation here, I would need the number of indexes where the prefix sum is greater than zero. So here the prefix sum is positive, 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 positive. Here it's negative. So it would be 1, 2, 3, 4, 5. So it should store 5 here, count of 5. Those would be the positions where my prefix sum is positive. That is, my graph is above the zero axis. So my PNT is another prefix array, which is storing the sum of number of points which are above zero up till index I. So till here, if we have something above zero, we are going to add plus. If we have something above zero, plus one, plus one, plus one, plus one. If we have below zero, plus zero. Okay. So the prefix sum of this thing would give us the count of number of indexes which are above zero till I. So those would be the positions where we have two options. So 2 to the power that would be our answer. 2 to the power that plus the remaining positions after the index I. So all of those positions, if you move the graph up, would be above the zero axis. This I explained because this is the minimum point. So we to compute this, we are going to require this prefix sum. So we are computing this thing. Okay. So this count. So count zero if our prefix of zero is negative. Okay. Like I'm storing opposite. I'm storing the negative. Okay. What I told here was here I was doing plus one plus zero. I'm doing opposite here. You can do like that also. in the final calculation, I will do that. Okay, so here I am doing plus 0, and I'm storing the count of negative uh, numbers. So number of numbers which are below 0, that I'm storing in CNT. Okay, so I minus that CNT would be those numbers which are above it. Okay, like you can directly do the numbers above it. You can directly store it greater than 0. That would be better. But like during the contest, I thought like that. So count 0 is just so if our prefix 0, if the first element is below 0, it's going to store 1 here, otherwise it's going to store 0. It's a boolean value. And then I'm running the loop, and my count I is count I minus 1. So the prefix I'm just doing plus the current value is if prefix I. If this current value of or if this current point is below the 0 axis, then we are going to add a plus 1, then add a plus 0. Okay, this is the first thing. We computed the CNT. Now what we are doing, we are going to compute the minimum element from the prefix array. Our minima point, the value of the minima point. Okay, so let me just erase everything so it's more clear. Okay, so now as I told, you have, let's say, two minima points. What would be the value of this minima point? It would be the minimum value in our prefix array. These are values represent our prefix array only. So the minimum value in our prefix array that I'm storing in a variable mn. So all those points where we are going to get mn, all those would be our minimum points. Okay. So if we have 2 points where we get the minimum value, we would consider for 2 of those points. If we get 3 points where there is this minimum value, we would consider 3 points, like 3 cases, and some of those 3 cases. Okay, so we found the minimum element is the minimum element function. All PR just means PR dot begin comma PR dot end. Okay, so if this minimum value is greater than 0, so this is the first case, like what I told you, like if initially only if you see the whole thing is the whole graph is above the 0 axis, there is no negative elements. In that case, we are just going to return 2 to the power n. So that is just base case I am considering. If this is greater than or equal to 0, or the minimum value is not reaching negative, then our answer would be just 2 to the power n. This is power is a modulo function. So if we have to take 2 to the power m, 2 to the power n modulo m. Okay, so we have to do mod m in each of those steps. So if you have to, we are just doing the binary exponentiation here. If you don't know about binary exponentiation, you can just go and learn about it. So I have written the binary exponentiation function where we are doing mod m in each step. Okay, so that's the 2 to the power n modulo m. Okay, the m I have taken, if you have any question, this is the m which was given with our question. That's our m. And just we are going to see out this answer and return. This base case is covered. Now what we have for the general case. For the general case, if the prefix I is not equal to mn, just continue. Okay, we are just going to count for the minima points. So if we get a minima point, then we are going to count. What we are going to count? C is n minus CNTI. Okay. Now what we can see. Okay, so what was this CNT1 here, which I was showing you? What was this CNT1? It was the, if you have this as the minima point, it was the sum of all those numbers above the 0 axis plus this full. So this can be written as total numbers are n minus this. That's also a way to write this. So that's what I've written. So in CNTI prefix, I had computed all those numbers which are below the 0 axis. So we can subtract those numbers from n to get those numbers which are where we have two options simply. So our C was n minus just CNTI simply. And our answer would be 2 to the power C for this case. So we are going to sum 2 to the power C to our answer. And this way, we are going to just see out answer and get a final answer. Okay, so I hope this is clear. If you have any doubts, you can ask. What if there are more than one points with same value? Okay, I have covered this. Uh, Now, do you have any more doubts in this, or is it clear? Like, I've tried to explain it like very well, but maybe this is a little tough to understand. So, if you have any doubts, you can ask, or we can move to the next question. So, like this graphical thinking, you can just imagine, like it was for the imagination part. Like, I in most of the problems, you can just take it as a tip. You can, when you have some numbers increasing, decreasing like that, you can just imagine it like this. So it would, for the imagination part and thinking part, it would make it simpler in your mind what you can do. Okay, that's why I just drew this I drew in my, like during the contest, this thing I just imagined in my mind and concluded this, that like we have to take the point. Okay, so this is a tip. So if this is clear, we can move to the next question, which is problem D. Okay, so let's move to the problem D. This is the last problem that we are going to discuss today. So you are given a string S consisting of lowercase Latin letters. Count the number of non-empty strings T not equal to A, such that it is possible to partition S into some substring satisfying the following condition. So, like we are given a string and we have to just partition this string into some substrings such that each substring either equals T or A. Okay, so and at least one substring equals T. This is the partition we have to do, and we have to count the number of non-empty strings T. So we have to count the number of those strings T which seg uh, to which we can partition this string such that these conditions are satisfied. That's our question. Okay. So like let's understand the question a little more. So we are given a string. Let's say A, B, B, C, A, B, B, C, something like this. Okay. What we have to do? We have to like partition this string into some parts. Let's say I partition this as here, 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 here. Okay. So if I partition this like this, we have to make sure. So first we have to select T, which is going to be a string. We have to select a string T and then partition this string. So let's say I selected BBC as T. Now we have to partition this string such that each substring is either this T, so such that each substring is either this T or A. So each substring should be either this or this. We have to partition this whole string in that way. That's the first condition, and the second condition is there should be at least one substring which is equal to T. Okay, we cannot have all A. At least one substring should be equal to T, and this T should not be equal to A. Okay, so if you look at this partitioning, what we have? We have an A here, satisfied. BBC here, which is T, satisfied. A here, satisfied, and then BBC here, satisfied. And we have at least one T here, so it's okay. So this partitioning is okay. So this T is a valid T where we can partition. Now we have to find the number of such T. How many such T we can have where we can get a valid partitioning of the string? That's our question. That's the what we have to find. Okay. So like this question was a little tough to think. Like I was kind of blank for an hour in the contest, but after that suddenly something clicked and I solved it. So okay, let's like look at how you can do this. So the first thing like I thought of is this A is creating a little bit of problem. So let's say I don't have any A in my string. Okay, let's consider this special case. I only have all non-A's in my string, BBC. Let's say I have this string where there is no A. Now, how can you calculate your answer? If you look at the constraints of the problem, it was that the size of the string was up to 2e5. Okay, so like any n square approach would not work here. So, what all t can you select so that you can partition this into? Now you don't have any A here. So whenever you partition this string, it would be of the form t t t something, either one time t or two time t or three time t, something like that. So what all t can you select so that you can partition this? If you think about it, so this the first thing you can think is if this string is of length of this string is 6, then what can be the length of my t? So if you take t of length say 4, so if you have a 4 length t and you add another 4 length t, it would become 8. And if you have only one t, it would become 4. You can never have 6 with the length of t as 4, because for this special case, you are only going to have this either 1t, 2t, 3t, or multiple t's concatenated together. That's what your string should be. So the first thing you can notice is the length of this t. The length of t should be, what should it be? Should be a factor of length of string, shouldn't it be? I'm considering this special case where there are no A. Okay. For this special case, we are just trying to calculate our answer. But then we will look at how can you manage that A in it. So if you have a string of length 6, we can have T of length either 1, we have 6 T's of length 1, or 2, or 3, or 6. That's the only thing. So all these are the factors of 6. If you have a T of length 4 or 5, it's not going to work. That is the first thing. If you have a string, just calculate the length of this. Let's say the length of this is n. Just go through all the factors of n. So how many factors do we have for a number? So if you know the approximate value for the number of factors of n, it is approximately the cube root of n. It is of the order cube root of n. If you didn't know about it, this is a very general information you should know, which is very useful sometimes. So if you just brute force through all these cube root of n values, and so this n was up to 2e5, so this cube root of n would be like less than 100. Okay, so you can just brute force through all these 100 values of n and just check for like all these 100 values of length, and for each length if you can check in O of n whether this is a possibility, then you can just compute in O of n into cube root of n, which would be somewhere around 1e7 for n 2e5. So this would be optimal to compute. So that's what we have to do. For this special case, we can actually go to all the factors of it. So for each len. So where len is a factor of n. Okay. So for each len, what we are going to do is, so at max there would be 100 values of len. like, okay, for each len. So let's say you have len equal to 2. Okay. So for a 6 length string, let's say we had this string only, which was BBC, BBC. So for this string, if the length of t is 2, if the length of t is 2, it means this first 2 is a substring, next 2 and next 2. This way we are going to partition this string. So it means this substring should be equal to this, should be equal to this. All these substrings are equal, we can have a valid string t. If all the substrings are not equal, we don't have, we don't do a count plus plus. So how can you check in O of n? You can just check, just take out the first substring of length len and compare it with all the remaining substrings of length len. And if you get any substring as unequal, just break your loop there. And if you just go through all those and all are equal, then just add a plus one to your counter. So in this way, you can just count the number of valid t's. So that's very simple. Okay, so we have considered the first case where we have no a's, then we can count it like that. Now, the problem is we have some a in between. So if we have BBC, AA, BBC, AA, now what are you going to do here? If you look at this, for that special case of BBC, BBC, we had only one option or two options. Sorry, we had two options here. So if you select length as 1, then this all are not equal. If you select length as 2, then BB is not equal to CB. If you select length as 3, then BBC is equal to BBC. So this would be valid. Then there is 6 as a factor. So if you select length as 6, then whole string is always a way to do this. This would also be valid. So there are two ways to do this. Okay. Now we have included some A's in between here. Okay. Now how many ways would we have? If you look at this, one way would be just select this, those two ways. Those two ways would still be valid. With a length 3, with BBC, you can select these two as T and less remaining A. You can just partition it them separately as A. So that way you can partition. That's one way. Okay. Another way is to uh, here you had selected BBC, this whole string. Now here you would have to include these A's in between if you have to select this whole string. So what we can do, we can select this as our T, BBC, AA, BBC. This can be selected as our T, and then these A can be partitioned separately. This is one more valid way. So these two ways would be valid. Now, what more can we have? We can, if you look at this, we can also have T as A, BBC. If you select this, you can select this also, A, BBC, and then this A and this A and this, these A's can be partitioned separately. That's one way. You can also select as A, B, B, C, A. Okay. So here you would select A, B, B, C, A this, A, B, B, C, A this, and then these two A's would be partitioned separately. Or you can also have here A, A, B, B, C. This can be one case. Okay. So in this you would have A, B, B, C, this thing, A, B, B, C, and then A, B, B, C, this thing, and these two A's would be partitioned separately. And one more possibility would be to take P equal to BBCAA. So in this case, you would have like this BBCAA, this much thing in one, and then BBCAA, this much thing in one, and these two A's will be partitioned separately. So these extra ways we are going to get if we add some A's in between here, other than that too. Okay. So can we count how many of these extras are there? Okay. So like we'll see how we can count. So, like, first thing from this observation, you would have observed that what we can do for any random string that we are given as input, we can just remove all the A's from that and form a new string. If we remove all the A's from that and if we form this new string BBC, then in this we can just this problem we have already solved above. How we can solve this? So if we have to just modify this problem by including the A's in between to make it compatible. Okay. So you can just form a new string. First step would be form like a new string with which has all the non-A characters. Form a new string with all the non-characters and check the length of this string. Okay. So the length of this string is suppose n. Okay. If the length of this string is n, then for t we are only going to go to the factors of n. We are going to go to all the factors of n. So these factors of n denoting the length of t is, for this case, this would not actually be the length of t, but the length of non-A characters in t. If you notice, all those t's which I have written, all those have the length of non-A characters is always 3, which is BBC here. So these are the sub cases of this 3 case. So these 3, in the initial one where we had no A's, then if 3 is valid, it means we do +1. But here, if 3 is valid, instead of +1, we actually have 1 as sorry, BBC is one case, which we considered already. And then we have 4 more cases. So we actually had a plus I for this 3. So now we just want to calculate how many plus we are going to do for each case. For the simple one, we had only +1 for each case. Now we won't have a simply +1. But what would we have? Let's see. So if you reduce this to a non-A string having length n, and then you're iterating through each factor of n. So let's say the one of the factors is len equal to 3. Now how would you compute this? So 3, it means it is going to have the first 3 non-A characters of this string. So BBC. So in the T, you are definitely going to have a BBC. That's certain. Okay. Now, how many A's can you? One way would be just take this BBC and just check. Can you make it with those? So you can ignore A's in the middle. You can just take them separately and just partition those A's separately. If BBC is here, BBC is here. So this is valid. Now we are going to like append A's either to the left of this or to the right of this. So here we appended one A to the left, one A to the left, one to the right. So two to the left, two to the right. So how many would we append in how many ways? So if you look at this, if you have a BBC here and a BBC here, to the left you have two A's to the left, which are free. You can take them. But if you're taking two A's to the left, this would also have two A's to the left at least. So you had two A's to the left. You can append two A's to the left. Now, to the right, if you see, it has two A's to the right. So you can append two A's to the right. But if you take two A's to the right and two A's to the left, both of them, all these are going to come into this. So these A would not be free for this. Okay, so you cannot have this BBC and AA. This would not be valid. So how many can you append to the left and how many to the right? So we can just see the first thing to the left, how many? At max, we would append the initial A's. So for the string, we can compute the initial A's. How many A are in the leftmost? Let's name it L. And to the rightmost, at the end, how many A's we have? Let's name it R. And then we can compute at the middle. So Here there were only two, okay, two T's, and the middle there were two A's. There may be multiple T's. So let's say a T here, a T here, a T here, and some A's in between, some A's in between, some A's in between. This way we are going to have. So to the left, this the count of this I'm telling it as L. The count of this I'm telling it as R, and these middle counts. So we take the minimum of this middle count, because if you have uh, to the right of T, let's say you have you appended y is to the right and x is to the left. So it would have x is to the left of this. So this y plus x should be less than equal to the number of a's in the middle. So this should be less than equal to, let's say I'm naming as m1, m2, and so on. This should be less than equal to m1. X plus y should be less than equal to m2. That's our case. These are our condition, and this x should be less than L. So x should be less than L, and this here you are going to have a y. So this is less than L, and this y should be less than R. So these are the cases you are going to get. Okay. So if you combine all these m1, m2, m3 in combination, you can write that x plus y is less than equal to min of mi, m1, m2, m3, all those the min. It should be less than all of them. So it should be less than the minimum of all of them. So like we can write these three cases, that x should be less than equal to L, where L is the leftmost, like leading is. Y should be less than equal to R, where R is the trailing is, you can say the rightmost extra is you have. And the x plus y should be less than equal to Mn. Let's say Mn we are saying as the minimum of the middle is. Okay. Mn is the minimum of the middle is. So these three conditions. So in how many ways can we have x and y? Okay. So we can have like x equal to 0, y equal to 0 would represent this string. Uh, X equal to 0, y equal to 0 represent this string. We have no a's to the left or right. X equal to 1, y equal to 0 represents this string. We have one a to the left. Here we have x equal to 1, y equal to 1. Here you have x equal to 2, y equal to 0. Here x equal to 0 and y equal to 2. These are the cases. So in how many xy pairs can we have satisfying these conditions would be our answer. How many xy pairs can we have? So for x, what's our condition? So like we can start by taking x equal to 0, then how many y's can we have? So if we take x equal to 0, our conditions become y should be less than equal to r, y should be less than equal to mn. So we take the min of those, say r is 7, mn is 5. So we can have y equal to, from 0 to 5, we can have anything. So 6 ways. So for x equal to 0, we are going to do plus 6. That's what we are going to do. Then we take x equal to 1, x equal to 1. So this becomes y less than equal to mn minus 1, and y less than equal to r is y less than equal to r is always there. So the min of these two plus 1 that we are going to add. Min of this was 5, then we had 6 ways, because y equal to 0 is also way. So that's what we are going to plus again. So we can just brute force through all the values of x and add the number of ways we can have y. So and so what the time complexity of this would be. So what's the value of x? So at max we are going to all the, like, at max we are going to up to L for x. So L is the count of the starting zeros, the starting A's in our string. So the whole length of this string is 1 5. Okay. So our actual code, that complexity was, if we say the length of this reduced string is n, then complexity of doing this, the initial thing was n into cube root of n. And to this, in each step, we are also doing the O of number of a's to the left. So if we have this whole, there is no A, then this n would go to 1e5. But if we have some A's, this would be reduced and this A would be added up. So the sum of those. So we are actually the going to be the sum of L. Okay. So for each for each root n step, the for each step, it's going to be uh, n plus L would be our complexity. This would be our complexity. No? So for each step, this n plus L is going to be at max the 1e5 only, the size of this. So this would still be okay for us. So we can just brute force through all the values, possible values of x. There is no problem. Okay, you can understand that. So that's what we are doing here. If you look at my code now, uh, this is my code for the problem D. Okay, so first we just took the string as the input and calculated the length of the string. Here n is the length of the full string. Okay, so what I am doing in the code, one more thing I would like to show. As I told, we are going to form a string with non-A characters. So instead of forming a new string with non-A characters, what I am doing is I'm storing the indexes of the non-A characters in a vector. So I'm doing a map. So let's see kind of a so it's a vector only, not a map, but I'm doing kind of a mapping thing. If you have this, if you look at the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So what we are doing, we would move. This is a A. This is a A. This is a non-A character. So we would in a map we would store the zeroth index of our non-A string. Would the actual index of that in our original string is 2. The first index of our non-A string, the actual of that is 3. The actual index of the second index of our non-A string, non-A string is this. Okay. 0, 1, 2, 3, 4, 5. So we are showing the actual indexes. So we have written 0, 1, 2, 3, 4, 5. These are the indexes in our new string, and these are the indexes in our original string corresponding to this. So 0, this B corresponds to this 2, this B corresponds to this 3, this C corresponds to this 4, this B corresponds to this 7, this B corresponds to 8 and 9. So this thing we are storing. So for this we are just taking a vector and appending the indexes of all the non-A strings. So these are the indexes of all the non-A strings. So in the vector, so vector the indexing is all already done with 0, and in the values we are storing this. So like this we can do the mapping of that. So vec of I represents just the index of uh, the ith element in our the second string. The index of that in our original string is given by. Okay. So this is the first thing we are doing, and then we took the size of this vec. The size of this vec would give us the length of non-A string, and then we are going to do the factorization of that. Okay, we took the size of that. So size was the vector size. So we appended. This is pushback. So all those characters which were not A, we appended the index of those to our vec, and then we took the size of that. And if the size is 0, so one special case you can see, if there is no, if all the characters are A, so in the special string we draw, it would be an empty string, there would be no. So we cannot do anything with that. So this special case we are considering differently. If you have all A's, what T can you select? You can select T is equal to A, you cannot select. You have to select at least A, or you can select A, triple A, or you can select 4 times A, or you can select the full array 5 times A. Okay. So if you have a string of length n, you would have actually 1, 2, 3, 4. So for a string of length 5, you had 4 options, except the A1. So you would have just, you can directly print n minus 1 here. Okay, for this special case where you have all A's. If the size is 0, that is you have all A's, you can just print minus 1 and return. This special case is considered only. Now let's factorize this size. So we are taking a vector factors and this in root of n, you can do the factorization and store those. And the maximum uh, size of these factors would be cube root of n. That thing we have told. So we have done the factorization here by going up till root of size, and these factors are stored in the array in the vector factors. So like we are just iterating through all the factors through the length. So len is the for each of the factors. We are taking them as the length and calculating. Like for calculating, one more thing I told was this L and R. So this L and R were the initial is and the ending is. Those were the count of those was length. So if you see what would be the count of initial is. So if the first non-A character is at index position 2, it means there are two A's in before. So just vec 0 would give us the value of L actually. And what would be the value of RB? So it would be number of factors to the right. So this is my N. So N minus this thing would give us this. So it would be N minus, this thing is N minus 1 actually. This is N minus 1. So N minus 1 minus vec of the last. So it's price minus 1. Okay, that's what I have written for R. So L is actually vec 0 directly. R is N minus vec of size minus 1 minus 1. So it's like N minus 1 minus that. Okay, so N minus 1 is the last index subtracted with the last index of vec. These would be the trailing A's, you can say. L and R is computed. Now answer is in rise to 0. We'll just plus our answer to this. Now we also have to find Mn, which is the minimum of those in between. Okay, Mn would be the minimum of the middle A's. Okay, so how we are going to compute this? So first, for like checking, we are going to take a substring from vec 0 to vec of len minus 1 minus 4. This is the len we are taking. Okay, so from vec 0 to vec len minus 1, we are going to take a substring. Okay, so we are taking a substring from vec 0 to vec len. This is our str, and we are going to check that for each of the substring, this should be equal to str from the next substring. So next substring from len up till size, we are going with I plus equal to len. Okay, so like my new substring would be as the substring from vec I to vec I plus len minus 1. This would be my new substring. So this S2, if this is not equal to str, we are just storing f equal to 0 and break and just continue. No need to check more. Okay, so like if it's unequal, it means we cannot have a t like this. All of those should be equal, like at minimum. And this mn, we are calculating the number of a's in between. A's in between will be vec of I minus vec of I minus 1. So a's in between, which will be, so if you have this, you need to count this b. Vec of this is 7, and so like this 4 and 7. If you had a c here at 4, at b at 7, so this spacing between 4 and 7 is a number of a's in between. So 7 minus 4 minus 1 would give us that, okay, number of a's in between. So that's what we are doing. Just vec I minus vec I minus 1 minus 1. Mean of those. So if this rule is satisfied without breaking the loop, then no problem. We are going to continue forward and we are going to iterate through each of the values of x. So x equal to 0 to x less than equal to min of like mn comma l. So each of the values of x, and then we are computing the value of y and answer plus equal to y. So, okay, this way we are computing our answer. And we are going to see our answer. So this was the explanation for the fourth problem. Okay. Mm, and written network after the second one. Okay, so yeah, these things were clear. The CBRT and is approx, yeah, is the approx value of the number of factors. Okay, so if you have any more doubt in this problem, you can ask. Like this is a little tough problem, so and if you are solving till here, I'm expecting a little like uh, you would be knowing some of the things, and like too much detailed explanation is not needed for you if you are solving till here. Then what I'm expecting, but if you have any more doubts, you can ask me. Okay, okay, no problem. You can just try the logic here, and then if you have any doubt, you can ask in query as you've written Weber. So okay, now if there is no more doubts in this, I can end the session now. Okay, thank you very much. We are going to end this.